In a previous video, we have developed this model for the facility location problem. We will now discuss that sometimes two seemingly different problems are closely related. Once your experience grows, your modeling skills will decidedly improve because you will be trained to discover more and more similarities among different models, which helps you to formulate new models. To start with, let's assume that all the x variables are fixed to either 0 or 1. Since the indices of the variables were chosen arbitrarily, let's suppose, without loss of generality, that the variables xi with I from 1 to k have the value 1, and the variables xi with I from k plus 1 to m have the value 0. To emphasize this, we can write our model like this. Now let's see what problem remains if we fix the x variables as mentioned before. Some of the x variables are 0. Consequently, the fourth term in the objective function becomes 0 and can be deleted. The third term in the objective function may not be 0, but it is a constant because all x variables are fixed. Hence we can delete this term too for the purpose of optimization, as shown in a previous video on model transformations. Because of the second constraint, if xi is 0 for I from k plus 1 to m, all qij with I in that range must be 0 too. Therefore, we can delete the second term in the objective function. We can delete all those qij's from the constraints . The remaining x's are 1, which simplifies the second constraint. And finally, since all x's are fixed, the x's are no decision variables anymore and the domain can be deleted. If you look closely, you'll see that the remaining model is a linear program and describes a transportation problem with k suppliers and n customers. Recall that transportation problems were discussed in a previous video. So we found out that if the binary variables of the facility location problem were fixed, the remaining problem would be a transportation problem. We could therefore say that the transportation problem is included in the facility location problem. Or, as most authors like to call it, the transportation problem is a subproblem of the facility location problem. This can be generalized, of course. Whenever we fix some decision variables in the model, the remaining model and the problem behind it would be called a subproblem of the original problem. Sometimes the reverse of what we did leads to a model for a problem. If you discover that a certain problem is a subproblem of the problem you want to model, you can start modeling the subproblem first and try to extend this model afterwards. The more experience you get, the more subproblems you will detect. Let's now have a look at another problem that was used as an example for big M formulations in a previous video, the simple lot sizing problem. Recall the situation briefly. In the lot sizing problem, we had a couple of t periods, say weeks, and demand for each period. In each period we can place an order which incurs a setup cost S per order. And if we order more than we need, some items must be kept on stock which incurs a holding cost H per item on stock at the end of a period. Now let's try to formulate a model for this problem that, as you will see, is different from the model you already know from a previous video. Knowing the facility location problem will help. Consider a period to be a location where a facility can be opened to serve demand. The term facility corresponds to what we called an order in the lot sizing world. The cost for opening such a facility in period I is Fi equals S. A facility at location I can serve the total demand in period J. The cost for doing so can be denoted by Cij. A few examples reveal how this cost should be defined. If a facility in period I meets the total demand in that very same period, the cost, the holding cost to be more precise, is 0. Hence, Cii equals 0. If a facility in period I meets the total demand in a period J greater than I, we have to keep the items on stock for J minus I periods. Hence, the cost to fulfill the total demand in period J with an order in period I is Cij equals J minus I times H times dj. But watch out! What is the value of Cij if j is smaller than I? Recall that in the simple lot sizing problem, back orders and shortages are not allowed. That means that an order in a period cannot meet demand in a previous period. To take this into account, we can use a modeling trick that we have already seen in the context of soft constraints in a previous video. Since we want to minimize cost, we can define Cij equal to m where m is a big number. If a feasible solution of the lot sizing problem exists, it won't be optimal to meet demand late. With these parameters, it becomes clear that the simple lot sizing problem can be seen as a facility location problem. Choosing the parameters of the facility location problem in a particular way makes the facility location problem become a lot sizing problem. The simple lot sizing problem is therefore a special case of the facility location problem. This too can be generalized. Whenever you can model a problem by choosing a very special set of parameters of another problem's model, your problem is a special case of the other problem. Discovering such relationships certainly helps to find a model formulation. In summary, we've got acquainted with two model relationships: subproblems and special cases. Do not mix up these two notions. If we fix some decision variables of a model, the remaining problem is a subproblem of the former. If we fix the parameters of a model in a particular way, the resulting model is a special case of the former.